All right, let's dive right in. Today, we're talking about something that's totally changing the game in cybersecurity, machine learning. As the bad guys get smarter and faster, our defenses have to do more than just keep up. They have to get ahead, and machine learning is how we're doing it.
I mean, really think about that for a second. The folks on the other side, the attackers, they never sleep. They're always coming up with new tricks, new exploits, new ways to get in. So how in the world are you supposed to build a defense that can actually adapt to that? That's the billion-dollar question we're tackling today.
Because let's be honest, the old way of doing things just doesn't cut it anymore. Setting up a firewall with a big list of "don't let this in," that's like building a wall when your enemy has already invented airplanes. The attacks today are so complex and so fast, we need a defense that can think on its feet. So, here's our game plan. First, we're going to look at why those old security models are breaking down. Then, we'll pop the hood and see how machines actually learn. After that, we'll see this stuff in action, like digital detectives on the case. We'll also cover the fuel for all this, which is data. And finally, we'll get into the really important stuff, the new rules of the game. Okay, so let's really set the stage here. The threat landscape today is just relentless. We're way past simple viruses. Now we're up against zero-day attacks that exploit vulnerabilities nobody even knows exist yet. Or even scarier, advanced persistent threats, where an attacker might be hiding inside a network for months, just watching. These are things that fly completely under the radar of old-school defenses. So, to fight an enemy that learns, we need a defense that learns too. And this is exactly where machine learning comes in. It's a total game changer. Instead of us having to write millions of rules by hand, ML models learn from data to spot patterns and make their own intelligent decisions. So, how do they pull that off? Well, the first way is called supervised learning. And honestly, the best way to think about it is like a student with a teacher. You give the machine a giant stack of flashcards, say thousands of emails, and on each card you've already written the correct answer, spam or not spam. The machine studies these examples over and over until it learns the patterns and can spot spam all on its own. But what if you don't have all the answers ahead of time? That's where unsupervised learning comes in. Is this like telling the student, okay, no teacher today, you just hand the machine a massive, messy pile of data with no labels, and its job is to find the hidden patterns and group similar things together all by itself? It's about discovering the unknown. So let's just put these two side by side to make it super clear. With supervised learning, you're working with labeled data, and your goal is to predict something, right? Like spam detection. But with unsupervised learning, you've got unlabeled data, and the goal is to discover something new, to find hidden groups. This is absolutely perfect for anomaly detection, finding that one weird thing that just doesn't fit in with everything else.
And then there's the third type, reinforcement learning. The easiest way to picture this is like training a dog. You have an agent, your puppy, and it takes actions. When it does something good, like sitting when you say sit, it gets a reward, a treat. When it does something bad, it gets a penalty. Over time, through tons of trial and error, it learns the best way to act to get the most treats.
Okay, so that's the theory. But now for the fun part. Let's see how these learning methods actually become digital detectives out in the real world, working 24/7 to protect our systems. So one of the biggest and most powerful uses for ML is anomaly detection. This is where those unsupervised models are the rock stars. They basically learn the unique rhythm of your network, what's normal for you. They learn who logs in when, where data usually goes, that sort of thing. And the second anything breaks that pattern, even slightly, it throws up a huge red flag. It can spot a potential threat before a human analyst ever could. Another massive one is malware classification. Just imagine being a security analyst. You're getting hit with thousands of new potential threats every single day. It's impossible to keep up. But with supervised learning, we can train a model on all the known types of malware, ransomware, Trojans, you name it. The model then automatically sorts and categorizes new threats as they come in, letting the human experts focus on what's most dangerous. It's a lifesaver. All these models and algorithms sound pretty amazing, right? But, and this is a huge but, what's the secret sauce that makes all of this work? Well, it all boils down to one thing: data. Without good, clean, high-quality data, even the most brilliant model is completely useless. You've probably heard that old saying, garbage in, garbage out. Well, in machine learning, that's not just a saying, it's the absolute, unbreakable law of the land. The quality of your model's decisions can never be better than the quality of the data it learned from. If you feed it junk, you're going to get junk back. End of story. So when we say quality data, what are we really talking about? It's more than just having a lot of it. The data has to be accurate, of course. It has to be complete, with no big holes, and it has to be relevant to the problem you're trying to solve. But maybe most importantly, especially in cybersecurity, it has to be timely. Data about threats from last year isn't going to help you stop an attack that was invented yesterday.
Okay, so all this power brings us to a really critical part of the conversation. It's not just about the tech. As we start to rely on these intelligent systems, we have to talk about the ethics, the responsibility, and the rules of the game.
So let me just ask a question that gets right to the heart of it. Can a piece of code, a mathematical algorithm, actually be biased? Oh, you bet it can. Absolutely. See, the models learn from the data we give them. So if that data has any of our own historical biases baked into it, say unfairly flagging traffic from a certain country, the model will learn that bias as a fact. And what's really dangerous is that it can even amplify that bias, leading to automated systems that make unfair or discriminatory decisions. And that brings up an even stickier question. When one of these AI systems gets it wrong, maybe it blocks an important, legitimate user, or worse, it fails to stop a major attack. Who's on the hook for that? Who's responsible? This is where we run into something called the black box problem. A lot of the most powerful AI models are so incredibly complex that even the people who built them don't fully understand why they make a specific decision. It's like a black box. Data goes in, an answer comes out, but the process in the middle is a mystery. And that makes it really, really hard to figure out what went wrong and who should be held accountable.
All right, let's wrap this up and hit the highlights. We've seen that machine learning gives us this incredible adaptive defense that we desperately need. We've talked about the main ways machines learn: supervised, unsupervised, and reinforcement. We know for a fact that high-quality data is the absolute fuel for this entire engine. But probably the most important thing to remember is this: a human has to stay in the loop. That oversight is what ensures these powerful tools are used fairly and that we remain accountable for their actions. And that really leaves us with one final and maybe the most important question to chew on. We're building these amazing, smart digital defenders. But as we give them more and more power, the real challenge for us, for all of us, is figuring out how we make sure our smart defenses also stay fair